So, of course, this material is not on the test. That would be kind of rude, right? Lecture on something and then test on it immediately afterwards. That would probably be bad form. But I want to talk to you for about 20 minutes here about what a function is and how we understand it. Okay? So, definition. We say f is a function from A to B, where A and B are sets, right? And write f colon A arrow B if for each x in A, we have f of x is a single element in B. So you can graph this idea sort of schematically to a couple different popular pictures to think about. This is one I usually go with. Here's A, over here's B, right? And I think about f as being a mapping that takes x and it maps it over here to f of x, right? Now, when A and B are subsets of the real numbers, right? So when A and B are both like subsets of real numbers, then this is said to be a function on R. Or you could say f is a real valued function of a real variable. All right. Furthermore, we say that the domain of f, which we'll also use DOM of f, that's the set A, all right? Whereas the codomain of f is, by definition, B. You probably have not seen codomain discussed before. All right? That might be something new for you. I don't know. Right? You've probably, though, seen the thing I'm about to write down, which is the range, right? What's the range? What's the range of the function equal to? That's y, right? Such that y is equal to f of x for some x in the domain of f. In other words, you could say it's f of x such that x is in the domain of f. The domain is the set of possible inputs. The range are the set of outputs which are actually attained. In contrast, the codomain, that's the universe in which the outputs go into. So in terms of a picture, the range could be smaller than B. Right? The range might only be like this part of it or something. So the range of the function can be a proper subset of the codomain. Now, customs. When working with functions on the reals, in other words, f goes from A to B, where A and B are both subsets of the reals, we sometimes define f by its rule or formula f of x. And so, and the custom is, this is the custom. We choose the domain of f equal to x in the reals, such that f of x makes a real output. Or in other words, such that f of x, I often will just say such that f of x makes sense, right? This is how we define the domain of a function. So, for example, if I had f of x equal to 1 over x, right? If that's my, I say, suppose we define a function by this rule, then what's the domain going to be? By custom, the domain of f is, the reals with 0 removed. So take the real numbers and get rid of 0. In other words, you could write that as minus infinity to 0, union with 0 to infinity. Right? Because the formula doesn't make sense when we divide by 0, right? Or another example, we could have f of x equal to the square root of, say, 2x minus 3, right? So in this case, the danger for the formula not making sense as a real number is that the input to the square root is what? Is negative, right? If it's negative, we're in trouble. So we need 2x minus 3 greater than or equal to 0, which tells me that 2x is greater than or equal to 3, which tells me that x is greater than or equal to 3 halves, which tells me that the domain of f is 3 halves to infinity. So as long as I take numbers larger than 3 halves, the formula makes sense. Great. Another example, f of x equals x to the 17th plus 3x squared minus 7. So this is an example of a polynomial function. This is a polynomial function of degree 17. Great. So what's the domain of f? So to answer that question, we have to ask the question, what x does this formula make sense for, right? When can you take a real number, take it to the 17th power, multiply, the square of it by 3 and subtract 7? I think you can think about it for a minute, but you should come to the conclusion, positive, negative, all numbers work, right? I mean, I don't think it would be particularly pleasant to calculate like f of 2 without a calculator, but you could do it. Anyway, so my point to you here is that the domain of f is just the whole real line. Right, so the domain of f in this case is just everything. Example 4. Actually, can you see down there? Probably not. Let me not do that. Example 4. We could have f of x equal to 1 over x squared plus 4x plus 5. Right? Then what's the danger? What's the danger? We've got division, right? So maybe there's division by 0. How can we be sure if there is or isn't? Complete the square. We have a winner. Yeah, completing the square will help us because that will show us more clearly that my worry that the denominator is 0 is unfounded. Because completing the square there gives us x plus 2 squared plus 1. And is there any way that the sum of two squared numbers can be 0? No, right? The smallest that can be is 1, in fact. So this reveals to me clearly that the domain of f is, again, everything. So over the next few lectures, we'll be talking about how to understand what the domain is and how to understand what the range is. Like figuring out the range for a function is harder, right? And one of our ultimate goals, of course, is to graph functions that are reasonable enough to graph. So far, everything I've written here we could graph with just a little time. But the other thing I should mention, definition. To evaluate a function means to plug in a value to the formula and find the output. Excuse me. So, excuse me. Throat's dry all of a sudden. So there's another picture that we like to use to describe how the function works. Like you can think about the function as sort of a machine, right? And you put x into the machine, right? And you get f of x out, right? A single thing, right? A function takes an input, it gives you an output, right? It's not like, it's kind of like a vending machine, right? You put in the money, you make your selection, and it gives you one thing, right? If it gives you more than one thing, it's malfunctioning, right? It's not a function. You're like, well, if it gives me more than one thing, who am I to object, right? I mean, but no, I mean, one thing in, one thing out. Now, let's see here. The other picture, or the symbol that we write is like x maps to f of x. This is another. This is red maps to. You could write like that. Right, so let me give you some examples of evaluation. So, excuse me. F of x equals to 1 over x, then f of 1/10 is what? It's 1 over 1/10. What's that equal to? One over 1/10 is what? 10, right? If we, I'll go with my second function, f of x equals to the square root of 2x minus 3, and so I could say f of I don't know, $100. What would f of 100 be? How's that work? We do square root of 2 times parentheses 100 minus 3, right? And so that would be the square root of, it looks like 197. But we can also evaluate functions at like symbols. We can evaluate functions at like symbolic expressions as well. So for example, if I was to say calculate f of Pac-Man, what would that be? That would be the square root, right, of twice Pac-Man minus 3. So sometimes we have questions where we're asked to like symbolically evaluate a function. In fact, that happens a lot in calculus. Like, for example, with my example 3, again, using f of x equal x to the 17th plus 3x squared minus 7, that one. Then if I was to calculate f of x plus h, what would that look like? We do x plus h to the 17th power minus 3 times parentheses x plus h squared minus 7. So sometimes we evaluate a function like symbolically.